Let's get going. Good afternoon, everybody. Welcome to spring, but really feels like winter, Monday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Hi. Hopefully, you all had a good couple of days since we last met. I did. Boy, have I been busy. Hopefully, you have been too. It's good being busy. Get things done. All right. Quick reminder, public service reminder from the management, me, and that is don't forget, if you want, do your extra credit project. It's totally optional, but if you send it to me, email me it before it's due, I can check to see if everything's okay. And if you do it okay, and have 10 entries that are all correct, you'll get 10. Yes, 10. 10 big points. Does this seem like it's coming out right at you? 10 points. And remember, it has to be organic molecules with at least one functional group that we discussed in our class. And it doesn't take that long to do it. I'd highly recommend look in your bathroom, look at the hand lotions, look at your bar soap, your liquid soap. There are a whole lot of things. Go down to your kitchen, look at the pantry, open up your refrigerator. Remember, any molecule you use must be on an ingredients label. Can't say banana has this because I've never seen an ingredients label on a banana. And don't forget, they don't all have to be different functional groups. They could all be alcohols, ketones, aldehydes, whatever, or any combination. But it has to be a functional group that we talked about in class. All right, coming attractions. A week from this Wednesday will be test 4, the final test, and not the final exam, the final test I'll be giving this class. And later in the week, I will post the point breakdown, how many pages on test number 4. And it will cover lipids, which are otherwise known as fats and oils, and then carbohydrates. I'll finish up with proteins and amino acids, but I'll just have a few points on the final exam, not on test number 4. So let's get started. I said today I would go through the lipids problem set, so I better do it. All right, everybody see lipid problem set on your board or on your screen? Give me a thumbs up. Thank you. All right, Dr. White's getting lazy at the end of the semester. C knows, that's cruel. What's a lipid? That's something that comes from a plant or animal, something that was alive, that's not soluble in water, but soluble in nonpolar solvents. Name one type of lipid. Well, fat is a lipid. An oil is a lipid. A steroid is a lipid. All right, time to make you work. Make you use your brain. Ooh, he's getting mean. All right, what functional group is in a fat or oil that's in a saponifiable lipid? And the answer is an ester. Remember, fats and oils are triglycerides. Triesters. All right, these are all things you should know how to do. Hint. All right, what's the difference between a fat and an oil? A fat is a solid or semi-solid at room temperature. An oil is a liquid at room temperature. For those who are wondering, room temperature is defined as 25 degrees C, which I believe is 77 degrees Fahrenheit. All right, what's yellow grease? pig's fat. Did I have it down here? Nope, I didn't. Let's do 2 more. I'm going to make you work today. Hey, here's 2 for you to think about. What is tallow? What is white grease? Ooh, someone was supposed to remind me about something, and they didn't. Snuggle bear. All right, what's tallow? You should know. That's beef fat. What's white grease? That's pig's fat. All right, I'm going to take a time out from the problem set to tell a story that I was requested to tell. All right, when I was working for a company that used tallow, white grease and yellow grease, Unichem Chemicals, when it was part of Unilever in the United States, that's also known as Lever Brothers. I think it's now just Unilever. I was a senior R&D and actually the lab manager. I was in charge of all quality control for a major chemical plant here in Chicago, plus all research in all of North America for Unichem, which was part of Unilever. And because of the level I was at, they had Unilever. Every once in a while, they had these really nice meetings, get together, senior research and development people outside of London. And I was invited to one. And I hadn't been working with the company for a while, not long, but I already made some big improvements that got everybody's attention worldwide, which is a good thing. So what you don't know is chemists know how to party hard, and we do, especially on company money. So anyways, we had this nice meeting, and one night we were staying at are you ready for this? The name of the inn we were staying at, I forgot where it was, outside of Manchester or London, one of those. It was called the Last Drop Inn. If you've ever been to England, the old inns and pubs have signs, wooden signs, pictures of it outside the front. And you know what the Last Drop Inn was named after? When you got hung. That's the last drop. But anyways, we had a nice banquet. Afterward, we're all in the bar area drinking, obviously. That's what you do in a bar. Not that I'm in any way implying those are things you should do. And I was with some of my colleagues who I already knew. And at that meeting and at the bar was the vice president of research and development for all of Unilever. Very important person, very powerful person. And one of my colleagues who I was drinking with said, do you know about the Snuggle Bear? Oh, I know it's on Downey, not Downey, Snuggle. Anyways, on Snuggle, duh. But anyways, Snuggle, but I don't know, what about it? Said, go over and ask Dr. So-and-so about it. And being the type of person who's not afraid of anybody, if you are, you shouldn't be at higher levels in industry. I went over, I said, you know, some people have been telling me you have a good story about the Snuggle Bear. He laughed and he said, let's get another drink and I'll tell you the story. And he did. And the story was when they were about to come out with Snuggle fabric softener, they were looking for some kind of logo or mascot to put on the box. And decided all the people in the company, Unilever, they had a competition. If you came up with the idea to what the put on the Snuggle box, you'll win. You get, I think it was 25,000. It was a lot of money. And one day he was about ready to go to work, and he was going to kiss his 4-year-old son goodbye. And he's holding the son, this old beat up teddy bear. All of a sudden, the guy said, "That's it." And he asked the son, "Can I have your teddy bear?" No, his son said, "It's my teddy bear." And he finally convinced him. He didn't tell me what he bribed him with, but he promised, "You'll get it back in a couple of days. I promise." So he took it to work, showed everybody, "This is our new logo." And lo and behold, it is. And that's the Snuggle beer story. And we had a good time that night. All right, back to work. Now, next one, give the organic product or products for the following reaction. And if we look over here, first thing you do, identify what's different. What's not a carbon-carbon single bond or carbon or hydrogen. And notice, ooh, an ester, another ester, another ester, and a double bond. Now, what are we reacting with? Sodium hydroxide and water. And sodium hydroxide and water will not react with a double bond, but it will react with an ester to give the alcohol and the carboxylate anion of the carboxylic acid you would have used to make that ester. And in this case, we've got 3 of them. So the first ester will give this alcohol plus this carboxylate anion. Notice the double bond is not touched. It's still there, and it should be. Remember, you also don't break carbon-carbon single bonds. No, 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 almost never. Next ester, you get this alcohol plus this carboxylate anion. And the final ester, you get this alcohol plus this carboxylate anion. All right, let's look at B. Same molecule now reacting with acid and water. And again, you have a double bond, but under these conditions, the double bond will not react with acid and water. Trust me, I've done this reaction. And the 3 esters will. Ester that you learned for test number 3, acid and water, you get back the alcohol and the carboxylic acid you would have used to make that ester. And ester number 1, we get this alcohol plus this carboxylic acid, double bond is still there. Ester number 2, we get this alcohol plus this carboxylic acid. And finally, ester number 3, we get this alcohol. So you get glycerin plus this carboxylic acid. All right, let's look at C. What are we doing? We're reacting this molecule with hydrogen catalyst. Well, you've got 3 functional groups, actually 4, 1, 2, 3 esters, and a double bond. Will an ester react with hydrogen and a catalyst under these conditions? No. You really got to crank it to make it happen. And I've never really done it either. It's not easy. But we have a double bond. And for test 1, you learn double bond has a pi bond sigma. You break the pi bond. Each atom of the double bond gets a hydrogen. And the catalyst, which I didn't put down here, can be nickel, platinum, or palladium. Here we have nickel. And the only thing that will change is the double bond. You break the pi bond. And notice I was nice enough to put look. Hopefully you did. And each carbon of the double bond gets a hydrogen. The rest is left alone. That's how you make hydrogenated fats and oils. Next, I have a double bond, same thing. I just changed the catalyst, so you're going to get the same right up here. Now, here we have this molecule reacting with steam. What's steam? Hot water. And remember, oops, somebody's got a question. Oh, you're welcome. You have steam, hot water. And as I mentioned before, there are three ways of, actually two ways, but there's subset of making a reaction go quicker. One is adjust the reaction temperature. The other is use a catalyst. In this case, instead of using acid and base with water, we're using hot water. And hold on one second. It's been a while since I looked this up. And if you look, we're talking like 400 degrees, 200 C, approximately for medium pressure, and it could be even higher, hotter pressure. Steam. While we're here, all right, thumbs up, people. Time for a little education. You see in the, I didn't even ask the question yet. You jumped the gun. You see the picture of the splitting tower on your screen? Now you can do it. Thank you. All right. Now, if you notice, this is a splitting tower, and it's a tower. And at the company I worked at in Chicago at the time, we had 5 of these, and each one was about 3 stories high as a 3-story building, quite high. And you could add processed water, steam, and the fat at the bottom. And they'd come together, and what would happen is at the bottom, you would get the glycerin. Now, what you don't know, but I do, and I'm going to teach you, see at the bottom where it says sweet water? That's the industry, and it was, I don't know how many eons it's been called that. That's what they call a mixture of glycerin and water from the splitter. I've never tasted it, and it was pretty crude looking. And then off the top, you would get your fatty acids. And we did this to the tune, all 5 of those, about 2 to 3 million pounds a week. We split like this in a splitting tower. And it was quite impressive. My job, one of them, was to make the quality of what they were making at the level that needed to be. And I worked with the plant manager to make sure the conditions in the splitting towers were correct, and also analyzed my group, the sweet water and the fatty acids at this stage were correct. Now, interesting, and I can't show you this, we had a proprietary system that the fatty acids were a mixture mainly saturated, unsaturated, which are mainly oleic and stearic, and we could separate each of those from each other. But I can't tell you about that unit. It's covered under a non-disclosure agreement, which I'm still covered by. I don't need to get sued. Never need to get sued. So in that tower, you'd be doing this, but with a fat or oil. And what is that? You get back the same as acid hydrolysis, the alcohol and carboxylic acid you would have used to make that ester. So if we look at this molecule, we have 3 esters. Ester number 1 gives me this alcohol plus this carboxylic acid. Notice the double bond is not touched. Ester number 2 gives me this alcohol and this carboxylic acid. And finally, ester number 3 gives me this alcohol, even though it looks like 2 parallel lines on the oxygen, that's really a funky looking hydrogen. And you get glycerin and you get this last carboxylic acid. Now, in real life, in these problems like E, that's just a pseudo molecule I made up for you to practice. Now, let's look at F. If you take yellow grease and acid and water, what are the organic products? Remember, for yellow grease, white grease, and tallow, pig's fat and beef fat, we have this representation where R sub S is the R group on stearic acid. R sub O is oleic acid R group. And again, I have the stearic acid R sub S R group. And this is a good representation of white grease, yellow grease, and tallow. And when you do that, the first ester gives me this alcohol. Notice ester, acid, and water. You get back the alcohol and the carboxylic acid you would have used to make that ester. And we get stearic acid. The second ester gives me this alcohol. The R group is R sub O, and I get oleic acid. And the final one gives me this alcohol, plus I get stearic acid again. Oops, I forgot to put the 2 for those who need it, but you don't need it. And there, the 3 products are glycerin, stearic acid, and oleic acid. And if you do it with tallow, same reaction, same answer. And if you do it with white grease, again, this is the same representative triglyceride, and you get the same answer. Now, how do I know this is true? Because the company I just talked about where I worked with that splitter, we got the same products essentially with white grease, yellow grease, or tallow. Now, it turns out, and I don't think it's changed, but I might be wrong, but usually tallow is the triglyceride that's available the most pound-wise in the United States. Next, yellow and white grease. And because of that, we use them interchangeably. When we being the purchasing manager could get yellow grease, white grease, we'd use that because that was always a few pennies less per pound than tallow. Now, when you're buying 150, 200 million pounds a year, 5 cents a pound, that's a lot of money. I'll let you do the math. Ooh, that reminds me, another story. Time for me to gross everybody out. Not really, at least I hope not. When a chemical company buys something to use in its facilities, a chemical, it gets what's known as a certificate of analysis. And in a contract, you have, I want to buy from you, we need this quality, and the company is selling it. Well, we can sell you this quality. You agree on the quality. It's written on a test and in a contract. And when they ship it, they provide a certificate of analysis. Well, if you're a good chemical company and you got somebody good leading your quality control lab, most do, you're going to check it yourself too, some of it, to make sure you're not getting garbage, because that's going to give you a lot of headaches. And with tallow, white grease and yellow grease, there were a couple of important specifications. And one of them, are you ready for this, was the percent hair, skin, and teeth. We're talking, where the beef fat and tallow came from. Yep, cows and pigs. Now, there was another one, which I just remembered. Let's see if I still have it on. I do. What they don't, they sort of show you is each one of these, there are a number of plates here. They have like a little dome that helps separate the liquid and disperse it. So there's a hole in the plate and a little hat on top. Well, important specification, very important, is the percent of, polyethylene in the fat or oil, or the white grease, yellow grease, tallow. Polyethylene? What the heck? How could polyethylene be an animal fat? Well, a lot of the fat that was purchased by rendering companies that turned it into pure fat, took the actual solid fat from the animals, got a lot of it from butcher shops. And what would they do? They'd be trimming a piece of meat, and where would they throw the fat? Into a garbage can. I don't know about your house, but my house does it. And you go to a butcher shop, and they have them too. The garbage cans have plastic liners. So the easiest thing to do is pull the drawstrings, throw it in the container for the renderers to pick up. And if the renderers are too lazy, they just render the fat along with the plastic. And turns out the plastic is soluble in the fat. Well, when it gets into the splitter, it clogs up the holes, and that can be very dangerous. And in fact, unfortunately, at the company I worked at, I don't know how it got in, or over years it built up, and they should have cleaned it out earlier. Even small amounts still build up. We had a bad fire. It actually melted the metal girders that held up that. And we lost, I think, 2 splitters. And it caused a lot of headaches for a while till we got them back online. And that was caused by the polyethylene, the plastic bags that the company we got our fat from didn't take out. After that, I lowered the level and had our purchasing agent work with our suppliers to even get the amount of polyethylene plastic from the garbage cans bags even lower. And after that, they never had a fire, thank goodness. Luckily, nobody was injured. All right. And if you notice, if you take tallow, you'll get the same thing. White grease, you'll get the same thing, because all 3 of them are this representation for my class. Now, let's look at yellow grease, steam. You get the carboxylic acid and the alcohol you would have used to make that ester. Well, if you use steam, you get the same products as acid hydrolysis, which would be glycerin and these 2 fatty acids, stearic and oleic acid. Quick question. I just remembered something. Did I talk about kosher certification in this for this class? If you can't remember, yeah, I didn't. I'll have to do that. We got, as I said last week, we're doing good time-wise, so I got time to do this where I thought I didn't, and probably didn't, I will. All right, same thing, white grease, same as for my class, tallow, and therefore you can use tallow. Now, K, yellow grease, sodium hydroxide, and water. And what do you get? Well, you've got a triglyceride, here it is, and it's really triester, ester, base, and water. You get back the alcohol, and the carboxylate anion, the carboxylic acid you would have used to make that ester, in this case, triglyceride. And the first ester, you get this alcohol plus sodium stearate. Second ester, you get this alcohol plus sodium oleate. And the third ester, you get this alcohol, meaning glycerin altogether, and you get sodium stearate, which I already have here. So those are the three products. And if you use white grease, you'll get the same thing, tallow. Now, give the organic starting materials for the following reaction. Yes, on test number 4, I will have at least 1, maybe 2 synthesis problems. If I were to put this on a test, this would be not 3 points, 6 points, because there are 3 different structures. And the question is, give the starting materials. What do you react with base and water to give? And here you could do name or draw the structure. I should have put that down. What do you do? What do you react with sodium hydroxide and water to get glycerin, sodium stearate, oleate, sodium stearate? And if we look up here, it can be yellow grease, tallow, or white grease. And finally, hidden all the way at the bottom, did everybody see what's the surfactant? No answer. That's a molecule that interacts with the different surfaces of different materials. And generally, it has a nonpolar head and nonpolar tail, polar head. All right, time for another Dr. White story. At that same company, the president of the company in the United States called me into his office. This was on the same site where I was located. And he had my boss with me, who was the vice president of technical. He was in charge of me. I reported him lab and research. The plant manager reported him, and the maintenance engineering manager reported to him. Great guy. Prat Dahmer's really great guy. Taught me how to be a senior manager. He was, for 6 months, I hated it. And then I finally realized he was always being honest with me. And he had said more than once, you know, I hired you because I know you can do the job. Now do it. And he taught me a lot. Well, anyways, I got called to the office, and the president said, you know, if we could sell our glycerin, because we took the sweet water and purified it to make USB glycerin, which is used in many things. And that was a cash stream, a profit margin area. And he said, if we could sell it as kosher, we could make a lot more money. So could you find out how you make that kosher? And the reason he asked me, which you already knew, was because I'm Jewish. And kosher is the Jewish dietary laws. And the number one first thing that kosher law, dietary law is, you can't eat anything with pork in it, or has ever been in contact in any way with food from a pig. Well, guess what? We're using white grease and yellow grease, which comes from pigs. I told them, all right, here's how you can do it. 2 ways. We wash out and steam clean every inch of our plant, and we stop buying yellow grease and white grease. He said, we can't do that. That's going to cost us a lot of extra money. Well, you want to know if we want to do kosher. That's the one thing. The other thing is build another plant that just keeps tallow in it. He said, that's going to cost a lot of money. Are you sure you're right? And I said, yeah, but I'll call up the Union of Orthodox Rabbis. It's one of the groups, organizations that certifies various things like food as kosher. I talked to the person in charge of that area, and he said, no, you are correct. I told the president. Now, quick little education. I think I might have done this, but if not, repetition is good for your education. And everybody see the kosher symbols, and there are various ones in the different parts of the United States and the world, but the most common one is Circle U, and that's Union of Orthodox Rabbis. Over here, let's see if I can find one. The Circle K, I believe, is the Care organization, another important one. And if I pull up, let's see, where do I hit? This doesn't have it. Well, it sort of does. I think, see the K inside of this little symbol right here, the lower left? That's the hood in the first letter of the Hebrew word kosher, which is, looks and right over here, the first word, that's Hebrew, you read left to right, that's kosher. See the little lines and dots underneath the letters? Those are the vowels. One of the toughest things was to prepare for your bar mitzvah because you had to learn how to read this. Not only it's a new alphabet, it's a new way of looking at it. By the way, this word, even though they have it underneath in English, Dr. White can read Hebrew and speak it a little, not as fluent as I used to be, but it's kosher lefpesach. And that means kosher for Passover, which we just finished. What would be the organic product or products for the following reaction? Your turn. Boy, time flies when you're having fun with white grease, yellow grease, and tallow. While you're doing that, everybody have this problem written down? I want to check something on the internet. Can't find it right now. Wow, the price is really up. It's at 73 cents per kilogram. Half of that would be divided by two, about 36, 37 cents per pound, like 33, 32 in the US. That's expensive. And I expected that because of the problems with everything going on today. All right, let's get back to work. All right, what do we have in here? A double bond. R sub O is oleic acid. And if we add hydrogen and a catalyst, you get rid of the double bond. Now, this has 18 carbons and one carbon-carbon double bond. Hydrogen and catalyst will not affect a carboxylic acid. Well, what were you going to get? 18 carbons and no double bond. And what is that? This is oleic acid in a shorthand form, and this is stearic acid. All right. All right, one other thing I like to cover that I didn't put in a problem set. You should know. You should know I don't spell well either. Did I ever tell you I was the first one down in spelling bee throughout grade school? It still hasn't changed. Leaving my class, I expect you to know how does soap work. And the first thing you should know, what's the structure of soap in general? And soap has a nonpolar tail and a polar head. And then what are you going to use when you try and wash your hands or anything else? Water. And water is polar, as you learned in the lab. And dirt and grease are nonpolar. And the important key to this puzzle is, and go to super large font because it's so important. If I were in a classroom, I'd do it half the size of a whiteboard. This is so important. And you should know the key to how soap works is light dissolves light. If I had a piece of dirt magnified, when we have the soap, because of light dissolves light, we have the nonpolar tail near the dirt and the polar head as far away from the dirt. And this goes all around at 360 degrees. And I'm not going to draw in another million of these. And this, you should know, is now called a micelle. And water looks, but you didn't know water molecules had eyes. They don't. But anyways, it sounds good. Looks at the micelle. And sees only the polar heads of the soap surrounding on the outside of the dirt. in the micelle and says, oh, micelle, I'm polar, you're polar. We know like dissolves like, so let's go down the drain together. And they do. And that's how you get the dirt off things like your hands or anything. I don't know about you, but I was probably the only one in Northern Illinois this morning taking a shower and thinking, wow, look at all the micelles I'm making to get myself clean. Probably was, but you should know this. And again, what should you know? What is the structure of soap? It has a non-polar tail and a polar head. You should know water is polar, dirt and grease are non-polar. And the most important thing, how soap works, you know it's important when I get the red arrows out, is like dissolves like. And remember, as we did in the lab, you did last week, things that are polar are soluble in polar things, things that are non-polar, soluble in non-polar things. In this case, because you have soap, has both a polar tail, non-polar tail, polar head. When it encounters dirt, it forms, and you should know, a micelle that has this structure, and that means the polar heads are on the outside, and water looks at the micelle and says, only sees the polar heads of the soap and says, I'm polar, you're polar, let's go down the drain together. And they do. So next time you wash your hands, think about you're making micelles. I think I might have mentioned this to you, but I'll mention it again. And if you see on your screen, let's see, you should see the different products that are all called micellar cleansing water or micellar whatever, cleansers and all that. And guess what? None of these contain micelles. They don't. But what they do contain, which I've been told by a number of my female students over the years, are, they don't tell me what it contains, just that the products work very well, especially removing makeup and other things from your face. It has very good soap formulation that's good at cleansing your face. And when you put it on and rub it, I think that's how you use it. You can tell Dr. White we use makeup all the time. But anyways, oh, it's crazy Monday, micelle day. But anyways, then you're forming micelle. But whoever came up with the name, it was great marketing, because there's no micelles in micellar water. Never have been, never will be. Because then you'd be buying dirty soap. Yeah. I don't think you'd want that. Oh my goodness. Time flies when you're having fun with snuggle bears and micelles. And with that, let's take a 5-minute break, and I'll see you after the break. Time to get started. I was just thinking of something I hadn't thought about in decades. Do you ever play hide and seek? Remember at the end where somebody would say, come out, wherever you are? Oh, memory from the past. All right, one other thing to talk about that I didn't do is you should know how to draw the structures of oleic acid and stearic acid. And you can't use R groups like R sub O, R sub S if I ask you to draw the structure. And you should know what is stearic acid? That's a molecule that's has 18 carbons, and it's a monosaturated, a saturated fatty acid, meaning no carbon-carbon double bonds. You should remember that too. And here's the structure of stearic acid. Now, when I allow shorthand, this is what we call R sub S. But when I ask for the structure, this is what you should draw. And oleic acid, you should know the structure of. It also has 18 carbons, including the carbonyl carbon. And the double bond is at C9. Notice the carbonyl carbon is 1 plus 7 is 8, which makes this carbon C9. And that double bond can be cis or trans. And if we're in a fat, you can have cis or trans fats and oils. And if you've been following the last decade, give or take a year, medical science has found that trans fats are not as good for you health-wise as cis fats. But as my doctor always reminds me, all fats you shouldn't have too much because cis or trans, they're not that good for you if you have too much. In other words, your triglycerides content of your blood is too high. And remember, what's the difference between a saturated, unsaturated fatty acid or fat? A carbon-carbon double bond. Saturated fatty acids and fats have no double bonds. Unsaturated have at least one carbon-carbon double bond. Now, don't say just double bond, because both have carbonyls, which is a carbon-oxygen double bond. Aren't you glad you have an instructor who works in this industry? Don't answer that. All right. Any questions on fats and oils? Ooh, I have one. Can you draw the ring skeleton for a steroid? Well, let me show you how. We went through this. This is something you should know. 6-membered ring. Next door, a fused 6-membered ring at 12 o'clock high on the second one. Another fused 6-membered ring, and next door, a 5-membered ring. That looks bad. Let's see if I can do a better one. A little better. This third ring looks funky. Sorry about that. It must be funky Monday ring drawing. I mean, never to say that again. All right. Any questions on fats and oils and steroids? All right, everybody see on your screen right now, cellulose and starch. In that case, now do you see it? Thank you. All right, both of these are polymers of glucose. Now here's a cyclic form of glucose. Now notice both of them have hydroxyl groups, carbons with OH groups, alcohols. And guess what? You can react those. Now, last week I showed you how acid hydrolysis in cows and horses and other animals can break down cellulose, cell walls of plants to make glucose, which is why you see cows, horses, elephants, and others eating grass and hay, which have cellulose. Now, because of the difference of the bond between the two molecules in cellulose, that type, and one's called alpha and one's called beta. If you're a carbohydrate chemist, you know that, and Dr. White really isn't. So I forgot which is which. In cellulose, that takes a long time. That's why you and I are not going to be kept alive eating hay, because our stomachs are too small. The time in our stomach and intestine is just not long enough to break it down, which is why cows have 4 stomachs and horses have huge stomachs and elephants have really huge stomachs. Now, what we can break down is starch, which is here. In both cases, you get glucose, which is the sugar in your blood. All right, hopefully you all see on your screen Wikipedia. You see the Wikipedia for cellophane? How many of you have ever, whoops, that's not what I wanted. How many of you have ever seen the candy that comes wrapped in that crinkly paper? Or if you get certain food, it's in a like a plastic wrap that's real crinkly. That's called cellophane. And how did it get its name? Don't know, other than it comes from cellulose. And how did he do that? Here's a simple form of cellulose, and you react it with sodium hydroxide. By the way, switch is totally off, and carbon disulfate. And you make this new molecule where you react some of the alcohols to make this. I have no idea what that is called, what functional group with the two sulfurs, the one on a carbon, thiol carboxylic acid. Nah, I don't know. But anyways, this material you can form into sheets or film that's used as the stuff like the crinkly stuff around certain candy. And that was discovered about 1900. Now, let's look at another one. And before I do this, let's go back to something you learned a while ago. If you take an alcohol and react it with ethylene oxide, you make this polyether. Here's our ether. And here's our alcohol. And you learned that for test number 2. Well, if you take cellulose, guess what? That has alcohols. And if you react it with ethylene oxide, you get this molecule. So everybody see that on your screen right now? And this inside here, with R was hydrogen, this is cellulose. Or you could use starch, was cheaper, use cellulose. And by reacting this alcohol here, here, and here with ethylene oxide, we have O, CH2, CH2, OH. Now, this makes the cellulose more water miscible. I don't know if soluble is the right term. And it can also affect how it hydrogen bonds to water. And hydroxyethyl cellulose, this molecule, is a very good thickening agent for water. And where is it used? One of the uses? Well, I'm getting to that stuff you'd never think I'd talk about. I think I already talked about it, but I'll do it again. And that is personal lubricant gel, one brand, KY gel. And what it essentially is water and hydroxyethyl cellulose. And it does a good job of thickening it up. And it's used in other things too. Like I said here, personal lubricants, they show some here, not KY. But anyways, this is your things, chemistry we've learned that are used today. All right. Now, as I mentioned last week, I'm way ahead of myself. We're in a good place as opposed to me rushing to try and get through before test number 4, because essentially I've covered all the material for test number 4. But what I like to do today is first have some fun, and then we'll go back and some things I might have rushed through on carbohydrates I'd like to cover today. So before we cover repeat of carbohydrates that will help you on test number 4, for whatever reason, I always think test number 4 should be the easiest, and students think that, and then they don't study hard, and guess what? They don't do as good as the other tests, and don't be in that boat. All right, what I'd like to show you, and the switch is totally off for test final or anything else, is what's the most important website, one of the most on the internet for me? Well, one is, and I think for a lot of you, is your favorite search engine. Mine is Google. The other one is the United States Patent and Trade Office website. Really? Yep. I spend a lot of time on there. There's a lot to learn from there. And what is that? First of all, if you don't know what a patent is a legal device that allows a person to claim what's called intellectual property. How many of you have heard in the old days where the miners, when they found gold, they staked their claim, this area of land is mine, and all the minerals on there are mine, like the gold. And that's called a claim. Well, how do you claim an idea? How do you claim a molecule? You use a patent. And a patent is a device, a legal document, I guess, that allows someone or a company to claim intellectual property. And they're patents for everything. I mean, everything. I think one time, I'll show you in a second, you can find patents for baseball bats, among other things. But in the chemical industry, again, the switch is totally off. There are three types of patents. One is called the composition of matter patent. And that type of patent, here's a new molecule. And when you have a patent, there are two things. One, it has to be unique. Somebody else can't have already patented or done it. And two, it has to have utility. In other words, it has to be used to do something. You just can't say, here's my idea, I'm going to patent it. You've got to show what's called utility. Well, the first type is composition of matter. Here's a molecule, nobody else has made it. I can show utility, it's mine. Patents are good for 20 years. That means for the next 20 years, once you get a patent, no one else can use that molecule or molecules if you have a composition of matter. Now, one thing that people don't realize with patents, when they say it's good for 20 years, you've got to protect your patent. And if somebody violates it, you got to take them to court and sue them, which costs money. You never want to be in a court of law for any reason. Even if you're going to win, you can still lose. All right. Second type is called the composition patent. That's where instead of having an original molecule, I say if I take this, and mix together, this mixture composition, that's got utility important, and that's mine if you get a patent. And the third one is a process patent. Composition of matter and composition patents are easy to protect. The last one isn't that easy, but still once in a while you need to get them. And that's called a process patent. And here's a molecule that's already been made, patented, and the patent is expired probably, or a composition, but usually it's a molecule, and you find a better way to make it. And once you get patented, you're the only one who can use that process. Now, let's go to does everybody see on their screen United States Patent and Trade Office website? This has been active since about, I want to say the mid-1990s, and this is important. And when you click on patents, you can see different things here. But what I like to do under learning and resources, I have this quick link, so I don't know where it is. So I'm going to cheat, go back to Google, and click on patent search. And then it takes me to everybody see search for patents. There are two types of search database they have. One are patents. These have been issued. Other are patent applications which have not been issued, but companies have filed. And let's look at patent full text. And notice under searching since 1976, you can have full text. And prior to that, you can just do the titles from 1790 through 1975 late. I'm going to click on the advanced search because I know how to do that. And you see this now interface. Now, they have different ways you can search. And if you look in help, if you click on the top, you'll see quick reference and how to do different types of searches. Now, I'm not going to teach you that, but I'm going to do a quick search. I'm going to look at all inventors with the last name White, who are in the state of Illinois and deal with sand. And sand has to be in that patent. And the important thing, this is a little older search box. You don't hit enter because that takes you to the next line. You actually have to click on search. And here they have some of the field codes you can search on. And here in all their patents back to 1976 are the ones that have that. And I'll pick on number, you click on the title to look what it is. I'm going to pick on number 7, ester cured binders. Everybody see that on your screen? Who's the inventor? Me. I hate to look at the date. That was in May of 2001. That's a while ago. Now, important thing about patents, at the top, they have the patent number 6,232,368, the day it was issued, the lead inventor, first inventor, and a title and an abstract. Then under that, the inventor. Now, this is important. Most people don't have the money to file patents or do the research. And when you go to work for a chemical company, you get paid a nice salary. Hopefully I did. And the first day, part of that day, once you get hired and the first day you show up, you spend with the lawyers signing all these legal documents. And an important one is that you assign anything you invent to the company you're working for, which is understandable. I have no problem with that. They're paying you to do this to help them make money. In this case, I was working for them. The name of the company was Borden Chemical. It's now called Hexion, still headquartered in Columbus. And here's my name and city, state, and also if you're out in the United States country. Now, any patents you referenced are here, and you can click on them and go back and look at them. And then if you notice claims, claims are where you set forth, like the old miners were, this is my land, everything on that land is mine. Well, here you claim molecules and other things. Now, this is the text. If you want to see a real patent, click on images. And this is what the actual patent looks like if you get a copy of, which Dr. White does have one. Again, you have the patent, the number, date of issue, the inventor, and this one they do show the country, the assignee, and the abstract. Now here, I'm clicking on full page to get a PDF of this. By the way, if you want, for $19.95 plus shipping and handling, I'll print out and send you an autographed copy. Not, but anyways, here's the actual patent. And it talks about the field of invention, the background, and then the summary, and then in detail. And notice I have a structure here where Z can be these things and R can be this. And it gets very complex. Now, at the very end, unlike the printed version, and also here are experiments to show utility that what I'm claiming it does, this mixture, it's a composition of matter, actually does that. And here we have our different claims. What is claimed, the curable binder with this composition. And then you have other claims that are underneath them that help further define other claims, like claim 2 defines further the composition of claim 1. This is all for legal reasons. Has a pH where 1 is acidic. Here's a specific example, and so on. And this is a patent. And these are very important. Companies like IBM, Apple, and all that have patents to protect their intellectual property. Everybody see the new patent with Keith and myself? Actually, my name should have been first, but I had a fight with my boss and he got back at me by putting my name second. And I didn't realize he did that till after this was issued. He and I had words after that. We were on speaking terms for a long time. Now, let's find out how much organic chemistry you've learned. If you look on mute, you hear me now? Was I on mute for all this time or just now? All right. All right. Everybody see the abstract and let me, what functional group is in that molecule? It's a quaternary ammonium salt. And why don't you read the abstract on your own first? Think about it. 6 months ago, could you have understood what that said? Probably not. Now you can't. You've learned organic chemistry. And like I said, this is the fun part of organic. This site is very, very useful. And I do a lot of research. I can learn about technology and things like that. Let's go back here. You have more than one, you can do string searches, patents back to 1976. And if I just have more than one word, or I want to find all patents with the term fabric softener in there, you put it in brackets, or not quotes, not brackets. Now, this is going to be a dump. And what I mean by a dump is, notice there are 5,500 patents, and they all deal with different types. And you can do even better. AS is assignee. I can refine it. No. All right, what did I do wrong? Let's go back here. I see, it should have been AN. Every once in a while, even Dr. White. And these are all the patents from Procter & Gamble that have the term fabric softener. And you can find out a lot of the things they're doing today. Notice this one, this relates to high efficiency particles of composition that liver situs, whatever that is. In other words, how do you know all the products they've come out with lately for your washing machines and dryers to make stuff smell good? This is patents for that. This work was done in Germany for Procter & Gamble, their division there. DE is Deutschland. And some of it was also done in Ohio, which I've been to that site. All right, I hope you all enjoyed that education of patents. If you ever have a chance, go to the USPTO search, patent search, and put in some terms. You can learn all about, it's amazing. I used to have a lab where the students had to do that, but they didn't like that, so I cut it out. All right, let's get back and do some review on carbohydrates. And the first thing, everybody see carbohydrates on your screen? Thumbs up, people. Thank you. All right, the first thing is you should know what is a carbohydrate. And that's a polyhydroxyaldehyde or polyhydroxyl ketone or compounds that yield such upon hydrolysis, adding water. Now, I showed you fructose and glucose and said you don't have to memorize these structures, but you should be familiar with them. And if we look at the top of glucose right here, three lines means identical, it has an aldehyde. And notice it has a lot of hydroxyl groups, alcohols. Now, if we look at fructose right here, you have a carbonyl attached to carbons here and here. And that's, as you learned a long time ago, that's a ketone. So you have in glucose an aldehyde, in fructose a ketone. Now I asked you to learn one disaccharide, and that is sucrose. And you should know sucrose is the common name for table sugar. Again, sucrose is the common name for table sugar. And if you put any sugar into your coffee, tea, or Captain Crunch or whatever, I don't think Captain Crunch needs any more sugar, but you might be a sugar freak. You're putting in sucrose. Let's do something quick. I've never looked this up. If you look, all right. some things I haven't taught you, but if you see on the left here, it has on the right, not the left, right, left. All right, get it right, Dr. White. I did. All right. If you look on the right, the IUPAC name is beta D fructopyranosyl alpha D glucopyranoside. You can tell I'm not a sugar chemist. And that's why we use common names. Sometimes the IUPAC names get, whoa. And when that happens, use a common name. Now, I don't have it on this slide, but let me remind you, sucrose is made up of a fructose and glucose molecule bonded together. And that's an acetal linkage or bond right here. Next, I talked about chirality. And you should know the Greek word, the word chirality comes from the Greek word handedness. And carbohydrates and other molecules exist in different forms, just like your right and left hands. And here we left to talk about mirror images. There's two types. I'll never ask you what's the superimposable or non-superimposable. Did I tell you about the spelling error I used to have on this slide? First year or two, I was teaching this. I had these slides like this. And one of the students finally said, you know, you don't have superimposable. I said, what do I have up there? It's superimpossible. I said, that's why students are having trouble with this. It's superimpossible. And I spelled it right and changed the spelling. So superimposable, mirror image, when you have two objects, you can superimpose them and all the points correspond. Non-superimposable is when you have two images that are mirror images and you try and push one into the other. It's no longer will be point to point. And then I talked about chiral objects. And a chiral object is an object that's not identical to its mirror image, otherwise known as non-superimposable mirror image. And an achiral, the letter A means without chirality, without handedness, and that means that's an object that is identical to its mirror image. It's superimposable. Now, just to remind you, your hands are chiral. And hopefully you all took your right hand, put it up to the mirror, saw the left hand without the ring on, unless you also had a ring on, the same ring on your right hand. And if I took the mirror image, mirror images, except for the ring, and big finger, center finger, superimpose. Oh, wait, the thumbs don't line up and the other fingers aren't right. All right, let's get the thumbs to line up. Now nothing else lines up. Your hands are mirror images, but they're not superimposable, so they are chiral. At this point, I asked you, and next Monday, today's Monday, next Monday, I will go through, hold on, let me do this. I'll go through the carbohydrate problem set. Also, how many of you want me to do a review again for test number 4? Give me a thumbs up. All right, back by popular demand. Next Monday, I will do my review for next test. In this case, test number 4. But let's have some fun. Two days later, I'll be finished. All right, your turn to have some fun. Are the following chiral or achiral? A right winter glove. B, a two-door car. C, a winter mitten with no leather palm. D, notice I haven't gotten winter out of my mind yet. It's still been cold. Hope you enjoyed summer on Saturday. That was it. But anyways, D, a round ball. And finally, E, a shirt with buttons, that should be buttons, in the front to the bottom of the shirt. In other words, buttons that go all the way to the top or bottom. For those of you who are women, you could say a blouse instead of a shirt. Your turn. I think we're going to go a little into the second break, but I'll let you out early because of that. Couple of minutes. By the way, I hope you all enjoyed your trip to the patent office. I don't know what they are now, but years ago, patents, just to go into a patent office, you have to spend, I think there's about 5,000 in filing fees, throw in the lawyer's fees, and people like me who do the research, patents can be very expensive. All right, everybody's done, so I better get to work. Well, as soon as you see the word right or left in description, immediately you know that's chiral. Just like your right hand, your left foot, those are chiral. Now, a two-car door, if you remember, I did the four-door car. And if you stand in front of a car and tell someone get in on the right or left side, they will know. And if you don't believe me, draw the mirror image of a car. I'm not going to make you break a rib laughing. And that's chiral. Now, a winter mitten, and you could do the same thing for socks with no leather palm, as opposed to a winter glove. Yes, you can laugh your head off. I'm never going to art school. Here's my mitten, the mirror image. Is this. I can take it, flip it over, and lay it. It's on itself. It's got a superimposable mirror image, which tells me it's achiral. If I have a perfectly round snowball, I'll only do an XY, but Z direction too. And this mirror image would be that. This, if I did it better, is superimposable on that. Something with a superimposable mirror image is, guess what? Achiral. Now, a shirt with buttons, I could do artwork, but I hurt some of you. If I did, that'd be so bad. You'd be laughing. But think about it. The shirt I'm wearing right now doesn't have buttons all the way to the bottom, but even if assume it did, look at the shirt. Oops. Now look at it. Oops. And I've got a left arm and a right shirt arm. And if I put my right arm in this side, this would be in the back and it'll look funny. And the front and back would be different. And shirts, the ones that you can, like this with buttons in the front, you can tell the difference between your right sleeve and your left sleeve. So if it has right and left, plus it has non-superimposed mirror image, it's chiral. And I would challenge you, when you have time and you're going around your house or wherever, look at things and say, are they chiral or achiral? And a lot of the things in our daily life are chiral, and a number of them are achiral. If this pen didn't have any writing on it, the writing might affect it, but let's assume it doesn't. The stylus, it's got a superimposable mirror image, and therefore it would be achiral, which you can use in either hand. I think so. Where did I read somewhere years ago? Don't they make handles for paintbrushes that are for right or left-handed people? And others that are just cylindrical are achiral. And if I look at the clock, it's time for a break. Let's take a five-minute break and come back, and we'll continue with going over important things you should know for test number 4. Time to get to work again. By the way, how do I look? Gave myself another haircut over the weekend. I've been to barber. He's a nice guy, but I haven't seen him. Oh, I wonder if he retired already because he was planning on it a couple of years ago. He was talking about it almost 2.5 years. Not bad for an amateur. All right, let's continue on. Now, the next thing when we're talking about chirality is a chiral center. And for this class, that would be a chiral carbon. And a chiral carbon is a molecule, atom in a molecule that has 4 different groups. And notice I have in blue tetrahedrally bonded. That means that carbon is only in a single bond. So how do you determine what carbons are chiral carbons? Well, it has 4 different groups or 4 different atoms or a combination of 4 different groups or atoms. And hopefully you're finding this useful. And why don't you try A? And then we'll do some more. All right, I think everybody's done. So let's take a look at this molecule. Now, how can you find the chiral carbons? Well, the way I like to do it is eliminate the ones that can't be chiral. If you have 2 or more of the same group or atom on a carbon, it can't be. So it's got 3 hydrogens, 2 hydrogens, 2 hydrogens, 3 hydrogens. It can't be chiral. Those are out. If a carbon is in a double or triple bond, whether the carbons or oxygen, a double bond to oxygen, I don't think you can have a triple bond to oxygen in an organic molecule. And therefore, these are out. So this leaves this carbon and this carbon to consider. This carbon right here has a hydrogen hydroxyl group. Right here, I'll call that R. And this whole thing on that carbon right here, R prime. And notice you have hydrogen hydroxyl group R and R prime, 4 different groups. It's chiral. Let's look at this carbon. It's got a hydrogen, bromine, a methyl group I'll call R, and this whole thing attached to it I'll call R prime. And notice the hydrogen, bromine, R prime, 4 different groups or atoms or combination, and that would be chiral. Oh, this was fun. Let's do another one. And here's one more. Remember, every intersectional line is a carbon here, 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 and here. Circle the chiral carbons. All right, let's do this. Everybody ready? Oh, I didn't do the poll. Let's have fun with the poll. And it looks like everybody's done, so I better get to work. All right, first thing like I say, not you say, I say is, what atom carbons have the same, 2 or more of the same on it? And the answer is this one right here and this one right here, 2 bromate. They're out. Which carbons are in a double or triple bond? Well, if you look at the top carbon, this aldehyde is really this. And this carbon is in a double bond to oxygen, so it can't have 4 different groups on it, so that's out. So that leaves us with the following carbons. 1, 2, 3, 4. Well, actually, 3. And if we look at this carbon as a hydroxyl group, hydrogen, this up here, R, and everything below it, R prime. So it has 4 different groups. Same thing with the next one, hydroxyl, hydrogen. Oh, I didn't want to do that. If we look at this carbon, I have this R group, hydroxyl group, hydrogen, and this. And notice that second circle is different from the top circle, so I can call that R prime, 4 different groups. This is chiral. And this last red carbon, same thing. And so those would be the 3 U circle. All right, let's continue. And hopefully that's a skill you'll master. Now, when we talk about molecules with things like chirality, that's called stereoisomers. And I'll never ask on a test, but isomers have the same molecular and structural formula, but differ in their orientation of atoms in space. And one type of special, well, you need a chiral center, and it's got to be rigid, can't be a nitrogen. One special type of isomers, stereoisomers, are enantiomers. And enantiomers, if I ask you to draw the enantiomer of this molecule, what I'm really asking is draw the mirror image. I always spell enantiomer wrong. If I did here, correct it on your own. I just made up a new sugar, probably has a name, but anyways, draw the enantiomer of that. Oh, let me give you a second one so you don't feel like you're being cheated. There you go. Draw the enantiomer of A and draw the enantiomer of B. And the reason I'm doing this is I wonder if I rushed through some of this the first time. I didn't do enough examples. Now I'm making up for when I rush through, and this should help. I hope so. If we're in a classroom, I could just look around, see when everybody's done, but not everybody has their video on or camera. All right, I better get to work. How do you draw the mirror image? You don't have to, but I found I like to put a little dotted line, pretend that's a mirror. Now, achiral carbons, you don't have to draw the mirror image. So the top aldehyde, you don't, but for those of you who do, it would look like this. You could have also drawn it like this. The bottom one, this here, same thing. You could draw it like this, or you could draw it like this. Doesn't matter. But the next 4 carbons you do. Let's look at this one. What's close to the mirror, you'll see first. And what's farthest away will be farthest away. Next one. What's close to the mirror, hydrogen. What's farthest away, hydroxyl group. Next to hydroxyl group. And what's farthest away is the hydrogen. And that's how you do it. Now, if we look at B, again, you don't have to, but I like to put in my mirror. This you could write this way because it's achiral. Same thing with the carbonyl. If you write it like that, that's okay. If you put it on the other side, that's okay. This right here, you could write like this, or you could write like that. Actually, realistically, the 2 should be on that side, but you know what I mean. But let's look at these 3 carbons, which are chiral. What's closest to the mirror? Hydrogen. What's farthest away? Hydroxyl group. Next carbon, what's close to the mirror? Hydroxyl group. What's farthest away? Hydrogen. Last carbon, what's closest to the mirror? Hydroxyl group. What's farthest away? Hydrogen. And that's how you do it. Now, one thing I haven't mentioned that I should have, and let's take a little time out for me to mention it. Anybody, hold on. Everybody got that copied down that wants to copy this down? Nobody yelling at me, stop, I'm still copying? Okay. And while I'm doing this, let me remind you today from 5 to 6:15, I'll have my office hour. And if you can't make it, need to talk to Dr. White, email me. And if I can, I'll set up another time when I can meet with you now. We're getting the end of the semester. Now, this is, if I did it correctly, and I believe I did, is glucose. I might have mentioned it, but I'll do it again now. Now, if you look at glucose, how many chiral carbons are there? Well, I'm going to circle them. 1, 2, 3, 4. Switches off, but there's still something interesting. And N is the number of chiral carbons. This formula, 2 to the nth power, equals the total number of isomers, all types. And for glucose, that's 2 to the 4th. That's 2 times 2 times 2 times 2, or 16. There's 16 possible isomers, some enantiomers, some others And this is just one of them, this structure called glucose. There are 15 others. What's amazing is Mother Nature picked just one. This is the only one because it had special properties. And this is amazing. Out of all those choices, 16, there's only one that's being used by Mother Nature. Amazing chemist, isn't she? I talked about Fisher projections, but that won't be on. I talked about DL conventions and optical activity. That won't be on tester to final. Now, one of the important things, which I came up with my little invention to make your life easier, don't tell anybody I'm being nice, is the cyclic forms that can form from glucose and fructose. And these are very important. Well, you say that about everything. Well, yeah, but if it wasn't for this, we wouldn't have starches in our daily life or plants, cellulose. Oh, look, it's Subtle Monday. Let's talk about hint, know this. All right, this is, in this case, glucose, a monosaccharide, and it's in equilibrium with something else. And let me remind you, you take a ketone or aldehyde plus an alcohol with acid catalyst. What happens? Keep your eye on the carbonyl carbon. That's where all the fun happens. What's attached to it? R prime. R prime can be hydrogen. And our double prime, you'll have an alkyl hydroxyl group, OR from the alcohol. And this is a hemiacetal, hemiketal. Now, if we look up here, here I have my aldehyde, and this is C5. This is 1, 2, 3, 4. Oh, I got it right, 5. And this hydroxyl group is this one right here, alcohol. And this attacks the carbonyl carbon of the aldehyde or ketone, which this does. And if we look at this, what's not involved in the reaction doesn't change. And that's the beauty of organic chemistry. Now, notice this hydroxyl group, which is this hydroxyl group or oxygen, bonds to the carbonyl right here. So I'm going to have this oxygen, Instead of having you learn Hawthorne projections, Dr. White's going to make the longest, ugliest looking carbon oxygen single bond from here all the way up here. And if you notice on here, you have hydrogen, hydroxyl. There's a hydrogen already there. And this is what you get. This is a hemicyclic form. I think it's called the glycosidic form of glucose, but I'll never ask that. But you should know how to do this. Let's take a look at what I did again. The general reaction here, ketone or aldehyde, alcohol, acid catalyst, you form the hemiacetal or hemiketal. Now, when it's in the same molecule, the alcohol in C5, the aldehyde here, you don't need a catalyst. And that's why also you have the equilibrium, arrows going back and forth. And again, this hydroxyl group attacks the carbonyl carbon, just like this right here, and forms this plus this. Well, this alcohol hydroxyl group bonds this oxygen, is this oxygen, which is this oxygen, which is this oxygen, to what was the carbonyl carbon, which is now this carbon. And there's going to be a hydrogen because R prime is H. And this so happens in here, these are connected together in this ring. And that's how you do it. Now, if we look at D-fructose, it has this structure. By the way, D-fructose is the sweetest sugar around. Let's say full fructose. And if you look at a lot of labels of things, especially food, you'll see, especially pop, you'll have high fructose corn syrup, which means it's this molecule. Well, let's take a look at this molecule. Whoops. And here again, we have a carbonyl, and that's a ketone. And on C5, we have an alcohol. And the same reaction occurs. This alcohol attacks the carbonyl carbon. Right there. And what's not involved in the reaction stays the same. This oxygen is this, and now it's going to be bonded to this carbon, which originally was the carbonyl carbon. And how did I get a hydrogen on there? Hold on. Oops. Sorry about that. Got carried away writing in my hydrogens. And if you notice, this carbon becomes this, will have a hydroxyl group on it, and it's got R prime, and this oxygen is from the OR. Again, you should know, if I give you this in a equilibrium, how to write the product. If I give you the product, you should know how to draw, or I might even put down how to put the name of the starting material, but you should know this. And again, both of these equilibrium are very important. In this case, glucose, the C5-hydroxyl reacts with the aldehyde to form this cyclic form. For fructose, this alcohol reacts with this carbonyl, the ketone, to form this cyclic form. And if these didn't happen, one of the things we wouldn't have is sucrose, table sugar. And I already showed you this, and I showed you the one with fructose. Now, we talked about reductions. And here's a problem. Give the organic product or products for the following. In case you forgot, I'll help you out. Oops, I better help myself out first. And your turn. While you're doing that, I'm going to go and find a show and tell if I can. I'll be right back. You work on this. Sorry about the delay. I was looking for if I could find real quick some over-the-counter stuff that I have that has the products you're making. I found they put some other sugars in there, like high fructose corn syrup. Not what? Let's do this. All right. If you look up here, and I assume everybody's done, will an alcohol react with hydrogen and a catalyst? Remember, catalysts can be nickel, platinum, or palladium. And the answer is no, you get no reaction. But with an aldehyde or ketone, you have. So whatever is not involved in the reaction is still there. But up here, I break this pi bond, and each atom of the double bond gets a hydrogen. And this molecule has a name, which you don't have to know, but it's called sorbitol. How it got that name, I have no idea. It's a common name, not an IUPAC name. And thumbs up, people. Give me a thumbs up. Can everybody see? This is not what I want. Hang in there. There you go. Everybody see sorbitol on your screen? Thank you, Christian. All right. And sorbitol is sweet, has no, and obtained from the reduction. Reduction is when you, for an organic chemistry, that's when you use hydrogen and catalyst of glucose. And it's found in many over-the-counter drugs. It's a sweetener. And I tried to find, oh, I didn't know that. It's a laxative. Anyways, and it's found as a humectant. Now, what's a humectant? I haven't talked about this. Certain molecules are humectants. They attract water, and they're usually polyols, many hydroxyl alcohols. And sorbitol is a humectant, and also what would be another one, glycerin, and there are other humectants. And how many of you have ever had those super soft cookies you can buy at the supermarket now? In fact, last night on the History Channel, they had a really nice history of foods in the United States. They had a nice thing about Famous Amos, and how he became famous and then lost his company and got it back again, or helped control it, make it better again. But anyways, those cookies have humectants, things that keep the water inside the cookie. Because when you first bake a cookie and it comes out of the oven and it warms, cools off a little, oh, it's nice and soft and so good, so good. That's because it still has moisture, water in it. With time, it evaporates and dries out, goes crack, and it's not as nice as fresh. Well, how do they keep it super chewy? And a lot of companies now make those type of cookies because Famous Amos made them famous. He was making, his company at one point was making millions of dollars, still does, being unique at that kind of cookie. Well, they put a chemical in there that's safe that keeps the water hydrogen bonded to it. And that's how they made it famous Amos, or how he became famous. Now, one of the things I talked about was how do you form a starch? And the reaction I talked about then was a modification of a reaction I taught you for test number 2. And if you have this, I didn't really teach you this reaction, but it's a modification of the second step of another reaction. You have a hemiacetal or hemiketal, and you react it with a different alcohol. You replace this hydroxyl group like this. And this is the basis for how we make all our starches and cellulose, polymers of glucose. And your turn. What would be the products or products of the following reaction? 3 points each. Your turn. And when you're done, give me a thumbs up emoji. Since there's just a small group of us left, because some of us had to leave for other personal stuff that goes on. Life happens, and I understand that. Thank you, David. Thank you, Vivian. And thank you, Christian. I better get to work. If we look right here, here we have this carbon, which is this carbon. So we have this functional group. We're reacting with this alcohol, hydroxyl group on a carbon. And this is our triple prime. This carbon here is this carbon right here, which will become this carbon. The only thing that changes is this to this. So everything that's not going to be involved in this chemical reaction, I will rewrite. And I have. And the only thing that changes is this to this. What's our triple prime oxygen and an ethyl group? And that's how you form linkages to make starch. But in this case, I'm just using a simple alcohol. Now, I said we'd end a couple minutes early because I went over and wanted a break, so I will. Let me remind you, don't forget the hand in the lab that's due this Wednesday. Second of all, don't forget today from 5 to 6:15, I have my office hour. If you have any questions, stop by, say hello. And finally, don't forget, as a public service to all of you, if you want, send me your extra credit project well in advance before it's due, because it's due on the 5th of May, which is a week from this Wednesday. And wow, where does this semester go already? Whoa. But anyways, and I'll check, and if there's anything wrong, I'll help you correct it. And with that, I'm done for today. I'll say, gang gesund. Goodbye.